Another concept that we need to consider when we're doing equilibrium calculations and we're looking at Q and K is to have a sense of the direction in which a reaction is going and how this might build into the Rice expression that we will be using to solve equilibrium constant. So I'm going to go ahead and write down my favorite chemical reaction right here, the Haber process. And K for this is going to be equal to 3.8. This is the value I'm going to define for it. Now, what we have to appreciate is that when we set up this Rice expression here, we can have the initial concentrations, the change, and then the equilibrium concentrations. This reaction has the ability to shift to the right, or it has the ability to shift to the left. That's all it can do. If it shifts to the right, then that must mean then the amount of hydrogen and nitrogen is going to go down, and the amount of ammonia is going to go up. So I can automatically know that before I even look at any of the numbers, I need to put minus, minus, and plus here if this is an example of a reaction in which we're going to the right. Conversely, I could have a reaction going to the left. If the reaction is going to the left, then sure enough, I would write it this way, where the amount of the ammonia is going down and the amount of the nitrogen and the hydrogen are going up. So anytime you set up a Rice expression and it's time to do the calculation for it, the first thing you're going to have to figure out is whether the reaction shifts left or right, and knowing whether it shifts left or right will allow you to write minuses on the left-hand side and positives on the right, or minuses on the right-hand side and negatives on the positives on the left. So let's go ahead and look at a few examples of what I've just shown you here. In this first case right here, as we're comparing Q and K and figuring out whether a reaction shifts left or right, here is my starting material. Now, we don't actually have to do a Q versus K calculation to figure out what's going on. We can simply see that because I have all stuff on the left and no stuff on the right, that there's only one way this reaction can go, because you obviously can't go this way when there's nothing to go that way. So this reaction must shift to the right, which means that I have minuses for the hydrogen and nitrogen getting smaller and a positive for the ammonia getting larger. If you wanted to look at it in the context of a Q value relative to K, the value for Q is the stuff on the right over the stuff on the left, and you end up with a value for this of 0. Well, let's look at another example, an example where we start with everything on the right-hand side, an example where we start with all ammonia in this case and no hydrogen or nitrogen. Once again, we have a situation where we don't really have to do any mathematical calculations to figure out the answer. There's only one way this reaction can shift, and that is to the left, which means that the ammonia has to go down and the hydrogen and the nitrogen have to go up. But I can do a Q versus K calculation that will show me the same thing. In this particular case here, I have Q, which would be 1 squared divided by 0 on the left-hand side. In other words, Q is infinity. It's a value larger than K, and as a result, because Q is greater than K, I know the reaction has to shift to the left. Negative value for the stuff on the right, positive values for the stuff on the left. Now, where it actually matters that I do the calculation of Q versus K is in those cases where I give you some of everything. And so as you take a look at this particular example here, I've got 1 atmosphere of hydrogen, 1 atmosphere of nitrogen, and 1 atmosphere of ammonia to start. And I want to know whether this reaction shifts left or right. Intuitively, you can't just look at this and know. You're going to have to go ahead and figure out what Q is and compare it to K. Well, Q, because I've so cleverly made everything equal to 1, is some pretty simple math. It's going to be Q equals 1 squared divided by 1 cubed times 1 is equal to 1. So Q is equal to 1. And if you remember, K is equal to 3.8. So in this particular case, Q is less than K. 1 is less than 3.8, which means that this reaction has to shift to the right so that Q can become more and more like K. That can only happen if the amount of ammonia gets larger and the amount of the hydrogen and the nitrogen gets smaller. So I have minus signs for the stuff on the left and a positive sign for the stuff on the right. these three examples in which I compare Q to K for the two extreme cases, all stuff on the left to start, all stuff on the right to start, and something in between. These Q versus K examples are things you have to do in every chemical equilibrium calculation you make, because you always have to know whether you're adding or subtracting the amount of stuff that's changing in a reaction. And there's no shortcut to know that. You have to do this middle step before you can get to the equilibrium concentrations.